Hey, welcome back to Fat Mama Physics. In this video, we're moving on to nuclear fission fusion for looking at mass effect and binding energy. So here we just have a quick table here just to show us a few relationships. If a reaction were to just happen spontaneously, it means that it is not stable. It needs to react in order to release all that energy. So that's why energy is going to be released. And because of that, your products are going to have a little bit more binding energy than compared to your reactants. Because with more binding energy, it means your products are more stable. Okay, which is why they will have more binding energy. And where does that energy come from? Is going to come from the mass of your reactants. So the little bit of mass gets converted into energy, in which the mass defect or the mass difference here is going to be positive. And you're thinking, what? How is that positive? Final minus initial should be negative. It's just a definition issue. Here I have the mass difference is mass of reactants minus mass of products, the opposite of what you would expect, right? So you know what? That's not the important issue. As long as you understand that your final mass is going to be less than your initial mass, it's just a definition. On the other hand, for something that you have to, if a reaction doesn't occur naturally, it means that the reactants are already very stable. It means you have to put in energy to kickstart the reaction itself. So energy has to be given to it. So energy is absorbed by the system. Sometimes we call this artificial transmutation or a non-spontaneous reaction. Okay, which means that yes, reactants have more binding energy. They're more stable, and as a result, if you have to introduce more energy into the system, then your products are going to be less stable, meaning it's going to contain a little bit more mass. All that energy gets converted to mass, and with the mass difference being negative, what that means is just the products are going to have more mass than the reactants. That's it. Okay, so using this understanding, we are going to start off with example 1. In the transmutation of nitrogen-14 done by Rutherford, nitrogen nuclei were bombarded with alpha particles. This is nuclei, and the following reaction. So here are the nuclear masses of the following, and we want to calculate the maximum kinetic energy for the alpha particle bombarding the nitrogen nucleus, which means this, so it's a transmutation, meaning this reaction here is non-spontaneous. You need to put in energy for this reaction to occur. So what needs to happen is we need to compare the following. We need to compare the mass difference of all of these particles, and which means that the binding energy, the difference in the mass is going to give us exactly the minimum amount of energy we need in order for this reaction to occur. Any more energy inputted into this reaction is probably going to give us more kinetic energy of our products, which is not necessary. But to fulfill the minimum requirement of figuring out the mass defect, the mass difference, and using that to convert to energy is what we're going to do. So let's compare the masses, and since this is a non-spontaneous reaction, we know our products are going to have more mass. So what I'm going to do, I know the mass difference is taking reactants minus products. I'm going to do the opposite because I just want to work with a positive number. So my products are going to be oxygen, which is 16.999131 atomic mass units, not mu. And I'm going to add that of a proton. A proton, I'm going to go look in a data booklet. Data booklet here says 1.007276 for a proton. And I am going to subtract the alpha particle, which is 4.0026, as well as the nitrogen nuclei, which is 14.003074 atomic mass units. So after I add, I compare the differences, I get 7.33 times 10 to the power of negative 14 atomic mass units. So if I took this atomic mass unit and I multiply it by the equivalent energy, that's going to be the amount of energy that I need to input into my system to account for the additional mass that is in my products. So taking that, multiplying by the atomic mass unit, which is 931.5, I'm going to get 0.6827 ... which is going to round to, let's say, 2 sig figs, actually 3 is fine. 0.683 mega electron volts. There we go. Okay? Phew, that was the first question. All right. That was pretty short. Do I have time for another one? It's okay, I'm just going to end this video here. I'm going to do the next example in the next video, although I may combine the two examples together, or maybe I might not. Anyways, there we go. Hopefully you learned something from this question. I wish you best of luck. Thank you. Fan Mama Physics, signing out.